Homeostasis, chapter 13 in your textbook. Homeostasis, if I can make this thing work. There we go. An individual cannot live unless they can stay warm, find water, and find food. And this isn't just humans, of course. This is any mammals, any animals need to stay warm or at least stay the temperature that their body wants them to be to find food and to especially find water. The body maintains an elaborate monitoring system to ensure that the individual is aware of their thirst, their warmth, and their hunger. It is so important to the body that the body maintains several means of monitoring for each system, and this is known as a redundancy. The nervous system coordinates these regulatory systems. The brain closely monitors temperature, water supply, and nutrient supply by using a variety of neural and hormonal mechanisms to keep them within the critical range. If we have excess of any of these three, our bodies have ways of shedding the excess to maintain our level of homeostasis. This is usually done without our knowledge. Seeking either shelter, food, or water is to seek a primary need. This type of behavior is known as motivated behavior. The systems used to regulate temperature, body fluids, and metabolism are negative feedback systems. When an individual goes beyond a set point in the level for one of the primary needs, the brain is informed of the negative level, like a warning light on a gas gauge. It's me opening something to drink. Because we are constantly burning fuel, utilizing and breathing out liquid, and entering into different environments, the process of maintaining homeostasis is a constant balancing act. Losses that we must have, that we cannot get around, are known as obligatory losses, and they obviously require constant monitoring of primary need levels. Cooling not only slows the action of molecules, but it slows the chemical reactions in cells as well. Enzyme systems, and a good example is, and I just started noticing it this couple of years ago, but during the winter, my hair doesn't grow as fast. My fingernails don't grow as fast. I shave every day, and in the summertime, I have a pretty heavy beard to shave, but in the wintertime, and as it's getting colder, this is the fall, I don't have as much hair to shave. Enzyme systems in most mammals and birds are most efficient at normal temperatures. It's, of course, 98.6 for humans. It's about 102 for dogs. And it really all depends on the animal as to what the normal temperature is. Any higher temperature and protein molecules do not bind properly and thus cannot function as they should. At very high temperatures, the amino acids in the proteins break apart and begin to fuse together at random. The protein in the brain is especially susceptible to high temperatures. Prolonged high fever can cause brain centers that regulate heart rate to die, thus killing the patient. At very low temperatures, the cellular membranes are disrupted by the formation of ice molecules, and even when thawed, they cannot reform properly. Warm-blooded animals generate heat from the inside to keep themselves warm and thus are referred to as endotherms. Endotherms generate heat by burning food in the body and a process known as metabolism. This occurs especially with horses. We used to feed, we had a couple of horses up in Montana. And of course, up in Montana, it gets really cold. The wind blows pretty hard. And we get wind chills in the minus 30s up to the minus 60s. And yet we had these two horses, and they could stay alive. For one thing, they stayed out of the wind when it was blowing that hard. But even if the temperature was minus 30, they created enough heat themselves to keep themselves alive, to keep themselves warm enough. They stood close together. We had two of them, and they stood close together. They kept each other warm. The other thing that we did was we gave them more food to eat and richer food in the wintertime so that they could burn more calories. We gave them oats. We gave them more oats, and certainly In the wintertime, then we didn't give them any oats in the summertime. We let them graze, but we were able to keep them alive, to keep them from freezing to death by just giving them extra feed. Heat inside the body is measured in kilocalories. 1 kilocalorie is enough to heat is enough heat to raise the temperature of 1 liter of water 1 degree centigrade. An adult can burn as many as 600 kilocalories per hour with strenuous exercise, but only 60 kilocalories when they're resting. So if you're sedentary and you're just sitting there like I am watching or putting this lecture together, I'm fairly sedentary. I'm probably only burning 60 or 70 calories an hour. Whereas today I looked at weights, I was probably burning about 600 calories that hour. So afterwards, I needed to replenish my calories. Otherwise, I wouldn't be able to function for the rest of the day. So I drank I drank a Code Red. Now, normally I'm drinking a zero sugar Code Red right now, so that I'm not taking any calories with this one. But the one I drank this afternoon, of course, had sugar in it, so I was taking in what 170 calories, I think, 210 or something. I don't know. And my rationale is that I needed to replace those calories, otherwise I wouldn't be very functional. At rest, the brain accounts for 1/3 of the heat generated by the body. As activity increases, the brain continues its level of heat production, but the muscles can increase their heat production tenfold. Humans can create heat by increasing metabolism, by breaking down brown adipose tissue, shivering, and increasing blood flow by constricting blood vessels. Brown adipose tissue is found around vital organs in the thorax, around the cervical and thoracic levels of the spinal cord. Under cold conditions, the sympathetic nervous system stimulates metabolism within brown adipose tissue, producing heat. And this is brown adipose tissue. This is not brown adipose tissue. That's just your body fat. This is the adipose tissue, the brown adipose tissue that surrounds your organs. And you have, no matter how slender you are, and no matter how little body fat you have, you still have this brown adipose tissue. Now, this is not brown adipose. This is yellow adipose tissue, actually. And it is found in your gut. This is, that a little bit extra fat you have in front. That's what this stuff is, and it will keep you warm. That's for sure. But this is the stuff that burns. It's really hard to burn this stuff. It's really hard to get your body to burn this stuff. It's not that hard to get your body to burn the brown adipose tissue. Humans start shivering at 36.5 degrees centigrade or 97.7 degrees Fahrenheit, which starts in the face and it spreads downward. When the human body is hotter than is safe for the individual well-being, brain cells can very quickly be adversely affected if the temperature isn't controlled. The body can cool itself through accelerated respiration or panting, perspiration to cool the skin, dilation of blood vessels to release heat through the skin's surface. The human body doesn't seem to have just one thermostat, but three: the hypothalamus, the skin surface, and the body's core, primarily everything but arms and legs. And this is the body's core right here. And this is, of course, the skin, and that's the hypothalamus. So each one will try to tell us how much, whether we're too hot or too cold. As evolutionary biologists point out, humans have the same concentration of salt in their body fluid as the oceans of the world. It is therefore assumed that humans evolved from creatures in the sea who had to maintain a fluid and salt content similar to that of the oceans. Thus, humans, as all animals, must not only monitor fluid levels, but salt levels as well. Osmosis is a special case of diffusion. In this case, a large molecule like starch is dissolved in water. The starch molecule is too large to pass through the pores in the cell membrane, so it cannot diffuse from one side of the membrane to the other. The water molecules can and do pass through the membrane. Hence, the membrane is said to be semi-permeable, since it allows some molecules to pass through, but not others. It won't allow the starch to go through, but it will allow the water to go through. So it's semi-permeable. Except for deionized water, other forms of water that we might take into our bodies is in the form of a solution, a mixture of molecules of solid molecules and water molecules. A solution in this case is referred to as a solvent, and the solid dissolved in it is referred to as a solute. Okay, so if you're drinking water, you've got Fuji water. Are you just drinking water? And the answer is no. There's also minerals in there. It's not deionized water. If you've ever tasted deionized water, it doesn't taste very good. Most of the water that you like to drink that tastes good to you has something in it. It has something. Usually it has minerals of one kind or another. Where I grew up in Indiana, we had iron in our water, and so if you got yourself a glass of water and you put it into the refrigerator and you let it sit there for 4 or 5 days, and then you drank it, there would be iron deposits on the side of the glass. That's how much iron we had in our water. So it always tasted a little bit metallic to me. The other thing that we had in Indiana was sulfur. There was sulfur in our water supply. We were in the middle of the state. Well, kind of. Anyway, there was sulfur in our water. So it smelled like rotten eggs to some extent. I could smell it, but nobody else seems to be able to smell it. I could certainly smell the sulfur in the water. So the water never really tasted very good to me. It tasted metallic because of the iron, which was obviously there, and it smelled vaguely like rotten eggs. And so I didn't really grow up liking the taste of water because a lot of the water that around where I lived didn't really have a very pleasant odor or a very pleasant taste as far as I was concerned. So people make fun of me because I don't drink water. And I tell them, well, water tastes like blood to me. And the reason water tastes like blood is because it's got iron in it. And blood's got iron in it, of course. It tastes fairly metallic if you've ever been punched in the mouth. And I have. Anyway, it tastes like blood to me. And I hate to tell you that. Those of you who just guzzle water by the gallons, but it really doesn't matter what water tastes like now, since I grew up drinking water with iron in it. Smells like rotten eggs. Semi-permeable membranes, and you can ask my brothers and sisters. My brothers and sisters, they think the water tastes fine. As a matter of fact, well, you grow up with something, you think it tastes good. That's the only flavor you've ever tasted, so you think it tastes good. But I never did, because I made the mistake of smelling the water. Should never smell what you're drinking, I guess. Semi-permeable membranes will block the passage of the solute, but allow the water molecules to pass freely from one side to the other. Remember, the solute is a solid form, whatever it is. In the case of the water where I lived, the solute was iron and sulfur. It had both iron and sulfur, and it had other stuff in it as well. But it wasn't the cleanest water in the world. It was from the well, and anybody else would say, yeah, it's fine. And it was fine. It's not like it had bacteria or anything in it. It just had iron and sulfur in it. The force, and people used to come from miles, hundreds of miles away to get bottles of our water because it was supposed to be so healthy for you because it had sulfur in it. Ugh. If you like drinking rotten eggs, go ahead. The force of pressure to pull water across a semi-permeable membrane is known as osmotic pressure. So the water comes out, but the solids stay on the other side. We refer to the concentration of solute in a solution as the solution's osmolality. Sodium chloride is a solute that the human body must balance in order to maintain a proper fluid balance. The human body must maintain a proper level of sodium chloride in order to function properly. That level of sodium chloride is 0.9%, or 9 grams of sodium chloride dissolved in a liter of water. 0.9%. So when I worked in the hospital, and I went into the emergency room, and they were giving somebody fluids. Usually, it was if the individual um, just needed fluids, they would give them normal saline. In other words, 0.9% um, salt dissolved in a liter of water. That's normal saline. And if you've ever had one of those IVs, you can taste it. You can taste the salt in your mouth when you get and it feels cold and it tastes cold. Well, maybe I'm crazy. Don't listen to me. This is referred to as an isotonic solution or normal saline, and of course saline means salt water. But that's what we give you in the IV. So if you need fluids, we'll probably give you normal saline rather than a unit of blood. We don't want to, you know, it's kind of dangerous to give you blood just because you need water. We'll just pump the normal saline to you. If you're dehydrated, we'll give you normal saline. A person who arrives in the ER severely dehydrated must be given fluids to replace the fluid rapidly. It's what I've been talking about. But if they just gave the person water through an IV, it would rapidly adjust the osmolality in your system. So what we have to do is give you normal saline to replace your fluids. In this case, the individual probably has more sodium chloride in their system than they need, and it is said to be hypertonic. So your system doesn't have enough water in it, and it has too much salt in it, and that makes it hypertonic. Too much water and not enough sodium chloride would make it hypotonic. Now you can do this to yourself if you're not careful. Some people, when they run marathons, they will hyperhydrate. They will drink a lot of water to begin with, and sometimes these people will kill themselves. How do they do that? Well, what they are doing is they are creating a hypotonic solution in their system, and they have too much water and not enough sodium chloride, and because of that, their system will break down. This is not normal to be what's it called? Hypernutremic is what it's called. Anyway, so just don't do that. Don't drink too much water. How much water is too much water? Well, you can feel it. That's a hypertonic. This is a red cell. This is what a normal red cell looks like. It looks like a donut, kind of. Okay, so a hypertonic means there's too much salt in the system, and it sucks the water out, and it collapses the cell, and this is what it looks like. Now, I've seen this under the microscope because I used to do CBCs, and one of the things you have to do is identify the red cells. Well, normally almost all the red cells look like this. This is what it's supposed to look like. But if you don't have it, if you're dehydrated, then you see some of the cells are crenated. Crenated means that they have collapsed, and it's a hypertonic solution. Your blood is hypertonic. Now, if there's too much water in your system, the hypernatremia, the hyperhydrated individual before they run the marathon, then the red cells, instead of looking like this, the oxygen actually is transported right here, this area right here. So this cell will transport oxygen. This cell will not transport oxygen. This cell will not transport oxygen. And now we got a problem. Now you got a really serious problem, especially if you're hypertonic, because now we have to give you salt, but it's really difficult to get salt into your system. And normally we don't catch you anyway. You think everything's fine, and you just collapse, and then we take you in, and we draw blood. And by the time we figure out what's going on, you're dead because you're not getting enough oxygen to your brain. Anyway, this is hypotonic. Too much water in your system, not enough salt. And if it's really bad, if it's really bad, then the cell will explode. Now we got a lot of problems. And this is, of course, what happens when you have a hypotonic solution in your blood. And I've seen all these cases. This one especially. That just means you're dehydrated. This is what I almost always see. And every once in a while, we'd come across somebody that was hypotonic, and we would, of course, see the blood cells. Actually, what we saw was the serum would turn yellow and red and yellow, pink and yellow. Internal cues that trigger thirst: hypovolemic thirst, thirst caused by low volume of fluid. Baroreceptors in the major blood vessels detect any pressure drop from fluid loss, usually caused by rapid loss of bodily fluids such as hemorrhaging, diarrhea, and vomiting. You think the worst thing that can happen to you is hemorrhaging, but the reality is you lose so much fluid when you have diarrhea, and it's going out. It's leaving you in a way that you have no clue of measuring how much you're actually losing. Vomiting, you're only vomiting what's in your stomach, but when you have diarrhea, you're losing all the fluids in your intestinal tract, and that's a lot. There's a lot of fluids in there. There's a lot of fluids right now wandering through your system, waiting either to be reabsorbed as nutrients and then taken back into your system, or defecated when you have a bowel movement. The vomiting, of course, you only lose what's in your stomach. Hemorrhaging, a little bit of blood looks like a lot of blood. It really, it looks like a pool of blood, but it's not. Usually, it's not. So, bleeding out doesn't really happen that often. But the biggest problem is diarrhea, because you really don't have any clue how much fluid you're actually losing. So this is hypovolemic thirst. Osmotic thirst, high volumes of solute in the extracellular fluid. Osmoreceptors in the brain detect any increased osmolality of extracellular fluid. Hypovolemic thirst, when baroreceptors detect a drop in blood pressure from tension on the artery walls, the information is relayed to the autonomic nervous system. The blood vessels constrict to maintain proper pressure for consciousness. And of course, if you don't remain conscious, then you go into shock. And this isn't good, because there's no way that you can physically think about maintaining yourself, because you've passed out. You're unconscious and you go into shock. The brain also releases vasopressin, antidiuretic hormone, from the posterior pituitary gland. Vasopressin acts on the kidneys to reduce flow of water to the bladder. Hypovolemic thirst and diabetes insipidus, vasopressin is not produced and the kidneys will not retain water. The patient is constantly thirsty, drinks lots of water, and urinates constantly. The urine tends to be almost completely clear, and this is in diabetes insipidus. Not as common as it used to be. Now we're seeing diabetes mellitus type 1 and 2 far more frequently than we see diabetes insipidus. The kidneys also detect the low blood volume and release a hormone called renin. Renin triggers a protein called angiotensinogen to form a protein, angiotensin 1, which in turn becomes angiotensin 2. Hypovolemic thirst, angiotensin 2 constricts blood vessels, triggers the release of vasopressin. It triggers the release of aldosterone. It acts on the preoptic area of the brain to elicit the feeling of thirst. This is accomplished in the subfornical organ, one of the circumventricular organs around the open areas or the ventricles of the brain, where the blood-brain barriers are weak. Osmotic thirst is more common than hypovolemic thirst. As the name suggests, it has to do with an imbalance of sodium chloride in the extracellular fluid due to loss of water. Osmotic thirst is caused from perspiration, respiration, and urination. Since we are dealing with an increase of sodium chloride in the system, this form of thirst can be triggered by eating salty foods. So if you ever have a craving for salty foods, do it. Go ahead and eat the salty foods because potentially you've got osmotic thirst and you've got too much water in your system. So go ahead and eat the salty foods. If you're really looking for a balance, if that's what you're seeking, then you won't have to eat very much salty foods before you come into homeostasis till you re-achieve homeostasis. Research shows that humans have osmoreceptors in various areas in the preoptic area: anterior hypothalamus, supraoptic nucleus, organum vasculosum of the lamina terminalis. Sodium chloride balance in the body is very delicate. As we have noted before, hypertonicity or hypotonicity will cause cell destruction. When angiotensin II is released in the bloodstream, it acts on the adrenal glands to release the mineralocorticoid steroid hormone aldosterone. Aldosterone acts on the kidneys to conserve sodium, which in turn allows the individual to conserve water in the body. More sodium, more H2O. This is one of the reasons why if you are trying to maintain your weight, what they tell you to do is to cut back on your sodium, because if you cut back on your sodium, you'll actually cut back on the water that you retain in your body. However, humans cannot drink seawater. It is hypertonic and thus adds more salt than water, causing greater thirst. This is one of the reasons why if you're dying of thirst on the ocean, you can't really drink the water. You try to drink the water, it just makes you hypertonic that much faster. While humans have not evolved to handle hypertonic conditions, creatures that live in the ocean or are able to survive with little water have kidneys that can handle large volumes of sodium chloride. Not only do organisms require water and warmth to survive, but they need food as an energy source. If this were the extent of our needs, humans could eat raw glucose and live very well. However, humans also require nutrients, chemicals that do not provide energy, but are required for the proper functioning of the body. Some of the nutrients that we require are in the form of amino acids. Of the 20 amino acids required by the body, 11 are manufactured internally, and 9 must be attained through our diet. These 9 are called the essential amino acids, these 9 amino acids. Besides the essential amino acids, our bodies require 15 vitamins, several minerals, and a few fatty acids from our food. But normally we get these with our food, so we really don't have to worry about it that much, unless you're not eating a very balanced diet. These nutrients are obtained when the body breaks down complex foods into simpler forms through the process of digestion. Most animals, especially humans, will build up stores of nutrients in their bodies. This is done because of our anthropologic ancestors tended to go through cycles of feast and famine, and the individual could not establish stores of excess nutrients, usually in the forms of fat, would not survive to reproduce. All the energy that we need to move, think, breathe, and maintain body temperature is derived in the same way. It is released as the chemical bonds of complex molecules are broken to form smaller, simpler compounds. To raise body temperature, we release the bond energy as heat. The amount of energy used is expressed in kilocalories. While not all foodstuffs provide energy, that which cannot be used is excreted, especially as solid waste. Available energy is used in one of 3 process activities: processing of newly ingested food. About 33% of our energy is utilized digesting this food. Basal metabolism, maintaining the body. About 55% of energy is utilized that way. And active behavioral process is only 12%. So when we talk about losing weight and the fact that we need to burn more calories, the exercise that we do only accounts for about 12% of the energy that we actually use. So you can only if you exercise excessively, you're still only going to lose about 12% of you're only going to use 12% of your energy for those activities. So what you have to do, you can't just diet and you can't just exercise. What you have to do is diet and exercise at the same time in order to lose weight. You can't just do one or because it won't work. You've got to do both of them at the same time. Okay, so if you're just dieting and not exercising, you're not going to lose any weight. If you're just exercising and not dieting, you're not going to lose any weight. What you have to do is both of them at the same time. Because the reality is that 88% of all of the energy that we use in our body are used to maintain our bodies. They're used in digestion and they're used in our basal metabolism. So the vast majority of our energy is used while we're asleep to maintain ourselves. And that's when our basal metabolism kicks in. And this is one of the reasons why if you weigh yourself before you go to bed, you'll weigh heavier than when you wake up the next morning because your basal metabolism has taken place and you will have lost that much more weight. So always weigh yourself in the morning. It makes you feel better. I always weigh myself after I exercise. That makes me feel better. I haven't eaten yet, and I just exercised, so I'm always lighter after I exercise anyway. It's probably all water anyway that I've lost. The body uses glucose as an energy source and so breaks everything eaten into this form. Glucose is stored in the body in the liver as a substance called glycogen. When ingested glucose is low, the body will release glycogen from the liver to keep the brain functioning. And this is the dieting I'm talking about. So if you are dieting, that means you're not taking in nearly as much glucose as you were before. Whether it's no matter what the food source is. No matter what the food source is, you're not taking in as much of it. And of course, you're still burning the same amount. Remember, 33% of your energy stores are used digesting your food, and 55% are used maintaining you. So if you take in fewer calories, then you're going to lose weight because it's going to call on your liver to break down some glycogen. When ingested glucose is low, the body will, of course, release glycogen from the liver to keep the brain functioning. The release and breakdown of glycogen from the liver is controlled by two enzymes from the pancreas. Glucagon promotes the breakdown of glycogen to glucose in a process known as glycogenolysis, and insulin, which promotes the conversion of glucose to glycogen. When an individual has been without food for a prolonged period, either forced or due to dieting, they begin converting their adipose tissue into glucose in a process known as gluconeogenesis. Gluconeogenesis. Wow, that's a tough one. At the same time, they will produce a secondary fuel called ketones, which can be used by the body and brain as fuel. Now, it's really kind of interesting because I can always tell when my wife is losing weight because I can smell ketones on her breath. Ketones smell, well, I can't really tell you what they smell like. They smell like bad breath. But you can tell if somebody has diabetes because they'll have ketones on their breath. I can tell when my wife's losing weight because of ketones. If somebody came into the lab and I had to draw their blood and I could smell ketones on them, I'd know they either had diabetes or they were trying to lose weight. They were dieting, as weird as that sounds. Long-term energy stores are in the form of fat cells or adipose tissue. Adipose tissue can be used for energy when the ready amount of glucose in the system has been depleted. Adipose tissue can be broken down into a simpler form, fatty acids, and glucose. Glucose is brought into the individual cells through glucose transporters in the cell membrane. Glucose transporters can only function when they interact with insulin, except for brain cells which do not need insulin to function. Otherwise, diabetes mellitus would cause such severe brain damage that it would be instantly deadly. Now, the reality is that if you have diabetes mellitus, your brain's still going to function anyway. Your brain is the last thing if something is starved for food, the brain is not going to be starved for food. It's the last thing that's going to be starved because it doesn't need insulin to break down. So if you're starving to death, your brain is going to be the last thing to be alive. There are 3 phases in the body that the body must go through to be able to utilize glucose in the diet: cephalic phase, the digestive phase, and the absorptive phase. The food itself acts as a stimuli. The sight of it, the smell of it, the taste of it, all of these things stimulate the body to start producing insulin. This evokes a conditioned release of insulin in the anticipation of glucose arrival into the blood. Just smelling the food, seeing the food, and of course tasting the food. The glucose isn't in your system yet, but just tasting the food will induce your body to produce insulin. In this phase, the release of insulin is regulated by the brain and is thus referred to as the cephalic phase. In the digestive phase, food entering the stomach and intestines causes the release of gut hormones. This stimulates the pancreas to release more insulin. During the absorptive phase, glucose enters the bloodstream, and special cells in the liver, the glucodetectors or glucostats, detect circulating glucose and signal the pancreas to release more insulin. More glucose, more insulin. Sorry, I needed a drink. Insulin allows the body to either utilize the glucose immediately or convert it into glycogen. The nerve that passes information from the liver to the brain and back to the pancreas is the vagus nerve. The vagus nerve runs to the nucleus of the solitary tract in the brainstem. And there you go, that's the vagus nerve, right? That yellow thing is in your heart and in your stomach and runs all the way into your brain. Diabetes mellitus, the lack of insulin causes a disease called diabetes mellitus. There are 2 types, type 1 and type 2. Type 1 we used to call juvenile onset. We're seeing more cases of type 1 diabetes in adults, and we had never seen this before. When I first started in medicine, it was extremely rare for somebody to develop type 1 diabetes. Usually they develop type 2 diabetes, but you never saw type 1 diabetes. If somebody had type 1 diabetes, they usually developed it right around, either they were born with it or they developed it right around puberty. But we never saw it in adults after they went through puberty. Type 1, or what we used to call juvenile onset diabetes mellitus, the pancreas stops producing insulin. Though the brain can still utilize glucose from the diet, the rest of the body can't, and so it utilizes fat stores instead. Since most of the dietary glucose cannot be used, it passes through the system and is excreted in the urine. Glucose can also not be converted to glycogen and stored in the liver. Diabetics are hungry because the body tells them to consume energy, but they can't gain weight because they do not store glucose as fat. Treatment is to provide exogenous insulin. Exogenous, of course, is insulin from the outside, not from endogenous would be inside, insulin from the inside. Exogenous is insulin from the outside. Diabetes mellitus type 2, adult onset diabetes, is a milder form of diabetes that usually does not affect an individual until they are adults. There are two causes of this type of diabetes. The cells gradually lose their sensitivity to insulin, and the body gradually decreases its production of glucose. This type of diabetes is more common among obese people and can usually be controlled by reducing the amount of glucose in the diet. The individual can also take medications that stimulate the pancreas to produce more insulin, and this is what metformin is. Many people prefer the foods that they grew up with. People are drawn to sweet foods and fatty foods because their taste is satisfying. People are also drawn to salty foods because we need the sodium chloride to maintain homeostasis. People who are hyperhydrated might actually crave salt. People develop taste aversions to foods that poison them and make them ill, and these are known as taste aversions. Most toxins are bitter tasting. Some people suffer from neophobia, the fear of new foods. One of the hormones released in the stomach and intestines is cholecystokinin, or CCK, which comes from the gallbladder. So cholecystokinin is released if foods have a high content of fat or proteins. Cholecystokinin also stimulates the pancreas to release insulin. Cholecystokinin may be one of the satiety signals. However, to inject cholecystokinin into someone as a means of controlling hunger causes nausea and cramping. Cholecystokinin in the presence of food activity activates the muscles of the intestines to work. Absence of food leads to feelings of nausea and cramping. So you don't want cholecystokinin into your system. Now, if you have gallbladder disease, you'll start pumping cholecystokinin into your stomach on a continual basis. And this, of course, makes you sick, makes you vomit, makes you nauseous, and it gives you cramps. My mother had gallbladder disease, and she had to have her gallbladder taken out. Now, back in the day when my mother needed her gallbladder taken out, they had to do an operation. They cut her thorax open, and they took out her gallbladder. Now they do it with 3 tiny little holes, and they go in there and they chop up the gallbladder and they suck it out through a tube. It's kind of cool, and you don't have that big long scar like my mother had right under her right breast. Hunger triggers. Low insulin in the blood is an obvious trigger to eat. However, high insulin levels do not equate to satiation. Satiety appears to spread over various regions in the brain, including the amygdaloid nuclei, the frontal cortex, and the substantia nigra. Leptin is a protein produced by fat cells that is secreted and informs the brain that the individual has had enough food. Obese people seem to be insensitive to leptin's message, and that is why they eat to excess. When leptin reaches the hypothalamic arcuate nucleus, it suppresses the release of several peptide neurotransmitters that induce eating, neuropeptide Y, and agouti-related peptide. Leptin also enhances the release of peptide alpha melanocyte stimulating hormone. Agouti-related peptide. You want to know what an agouti is? That's an agouti. An agouti is a South American rodent. So how in the world did they ever discover this? Well, of course, they've been working with agoutis for an extended length of time. And anyway, they got the two together, and that's what an agouti is. So what is it? Agouti-related peptide. Ugh, ugly. Anorexia nervosa and bulimia nervosa are 2 disorders of hunger management that leads to extreme emaciation and even death, especially in the case of anorexia nervosa. Anorexics commonly desire and think about food, but deny themselves sustenance. The basic problem seems to be a distorted body image where the individual sees themselves incorrectly as overweight when they are actually thin to the point of death. Anorexics tend to be slender of build to begin with, and the excessive dieting merely adds to emaciation. And there you go. Those are anorexics. Bulimics tend to be a little plumper than anorexics. Bulimics are able to control their weight by purging the food from their system, either through exercise, vomiting, or laxatives. Bulimics will also go a little crazy from time to time and eat massive amounts of food at one sitting and then relieve themselves of it through vomiting. This is known as binging and purging. And that is the end of the chapter. So I'll talk to you next week. I can't remember what next week is all about, but we'll figure it out.